reactions today. This is actually, I like many reactions, but this particular reaction is very near and dear to my heart. We're going to learn something called the Wittig reaction about how to make alkenes, and I probably personally run this reaction maybe 150 times or so when I was a graduate student getting my PhD. It's a very, very useful reaction. So we're going to cover that today. So all these learning objectives are going to talk about what's called the Wittig reaction, which is an olefination reaction. As I really like to not call things by their named reactions, as you know, I like to describe them more based on the functional groups. There's a lot of words we don't know about the Wittig reaction, so I'm going to call it the Wittig reaction just to actually simplify it. So that is one of the ones that the names are kind of important. All right, so the Wittig reaction, we have to start with something pretty specific. So as our starting material, we're going to make something called a phosphonium salt. So that's why it can be a little bit complicated, but this is learning objective 18O, right? And this is going to be the 4 P's of formation of Wittig reagents. So Wittig is spelled with a W. It's not pronounced Wittig, though. It's pronounced Wittig. It's somebody's last name. Right, and these are in particular phosphonium salts. So we haven't dealt with phosphine a lot, but that is element number 15. It's right under nitrogen. So much like nitrogen, it likes to have 3 bonds to it and a lone pair of electrons for the most part in its ground state. So we're going to make these phosphonium salts from phosphines and alkyl halides. All right. So we can use a lot of different phosphine salts, but for the purpose of this class, we're just going to focus on the most common one, which is triphenylphosphine. So triphenylphosphine is going to be our nucleophile in the reaction. I've suggestively drawn in that lone pair of electrons. So, you know, the naming convention is pretty similar to amines, right? If this was a amine, we might call it a triphenylamine, but here we have triphenylphosphine. Right, and our electrophile for this reaction is going to be an alkyl halide, but we specifically need to have at least 1 proton here. Right, and this is our electrophile. Okay, so this means a primary or secondary alkyl halide. Right, we're going to need to deprotonate a CH bond, and so later on in the reaction. So we need to have at least 1. This can't be a tertiary alkyl halide. You could make a Wittig reagent, but then you couldn't do the Wittig reaction. So I'll show you the mechanism, but this is just an SN2 mechanism. We have an alkyl halide. That's another reason why it needs to be a secondary primary, because we need to do the SN2 reaction. And what we end up with at the end of the day is triphenylphosphine that is now bound to our carbon with R1 and R2. And we'll just draw in our hydrogen there. So we call this phosphonium salt. Right, so IUM, right, we've seen ammonium, we've seen aminium. That's always meaning that we have a positively charged component of this. So we can draw this as a positive charge on our phosphine, and then when we displace this, we're going to have our X minus as our counterion. All right, so we've taken that lone pair of electrons on the phosphine and we've used it to make a base, to make a bond, and so that's why we're seeing our positively charged phosphine here. All right, so this is why it's a salt. All right, so now what we're going to do in this reaction is, as I suggested to you, we're going to do a deprotonation. So we need a base here. Some good choices for bases that we use in this reaction a lot are sodium methoxide, that's pretty common, and N-butyl lithium. All right, we have other options. We have to match the pKa, but if you just want to narrow it down to just a couple of bases, those are ones that work really well. So we have that CH bond, and this CH bond is now pretty acidic. Normally we don't deprotonate too many CH bonds, but this one's acidic because it is in the position next to this charged phosphine. And so when we have that charge, that electron density being pulled away, it becomes quite acidic. So then what we get out is that deprotonation. Our triphenylphosphine portion is still positively charged. All right, we haven't done anything to break that bond, but what we've done is we've deprotonated that CH bond, so we have a negative charge there. All right, and then we have our H bound to our base, which would be positively charged, and we can just carry our X minus throughout, right? So whatever our alkyl halide was. So this is the salt that gets deprotonated, and then we form this kind of interesting looking species here. We have not seen too many of our compounds have these charges where they're both cationic and anionic right next to each other. That's called an ylide, and we'll talk a little bit about that, but first I want to go into P4 for this. So luckily for you, this is mostly just chemistry. Oh, question. Great question. So for those who couldn't hear, why didn't the halide just come in and deprotonate this H here? So we need a little bit of a stronger base to do that. And so our halide, the pK of HCl versus like methanol or butane is just, it's a pK mismatch. So we weren't able to do that, but that's a great question. We often see our X minus coming in and deprotonating. So yeah, great question. All right, so let's talk about P4 here. Let's think about how we get here. So as I said, our triphenylphosphine is going to be our nucleophile. And we're going to have our alkyl halide as our electrophile. And in the first step, we're not going to do anything. I'm just going to arbitrarily say that alkyl halide is a bromide, for example. We're not going to go ahead and do anything with that proton yet, but first we get nucleophilic attack from the lone pair of electrons on our phosphine. We break this CBr bond, all right? Just an SN2 mechanism, right? We've seen this before. This is just SN2, nucleophilic substitution reaction. All right, so that means we're gonna get to our phosphonium salt intermediate here. We still have our H bound, we have R1 and R2. I'm not drawing any stereochemistry here, but we would, of course, have inversion of that stereocenter, but we don't need to worry about that in this case because that stereocenter is going to go away. All right, so here's our phosphonium salt that we saw before. And as I said, we can go ahead and think about a base deprotonating that CH bond. All right, I'm going to arbitrarily use N-butyl lithium. It's used by people all the time. I definitely used it for this particular reaction. And you'll recall that we need to start an arrow from electron density. So if you wanted to draw a lithium plus and a carbon minus, that's fine. Otherwise, we're going to take the electrons from the bond of the lithium carbon, and we're going to go ahead and deprotonate that CH bond, break that, and we're just going to leave a negative charge. Those electrons are going to sit where that CH bond was. All right, I'm going to draw this down so we have enough room. So now we get to our positively charged phosphine, our negatively charged carbon ion. So we can say that this is just a deprotonation. And this was enabled by having that positive charged phosphine. Right, so the first mechanism is just an SN2. That's the first step. And then the second step to form these Wittig reagents is just deprotonation. This is a super, super common reaction. So R1 and R2 are going to be so many things. All right. We're going to see a lot of different groups there, and we'll show some different examples as well. All right. And let me just include the counterions here. Sorry, I always like to have some bookkeeping purposes so you can understand what's going on. So go ahead and add those in. And then what we deprotonated is going to have a CH now. All right, so that's how we make these. It's just an SN2 followed by a deprotonation, right? A lot of mechanisms kind of are the same in organic chemistry, and you can start to recognize the pattern. Well, I have a nucleophile and an alkyl halide. You know, it's probably going to be SN1 or SN2. All right, so this is called an ylide. All right, YLIDE is the word ylide. And so this is kind of a funny looking molecule. So that's our next learning objective, is we're going to kind of define what this ylide is and how it works. So this is going to be learning objective 18P. That learning objective is to describe the structure and properties of ylides. Right, I mean, these are kind of interesting looking molecules that we haven't seen too much before. All right, so we have many different words when we have two types of charges in a single molecule. If there are two cations, we could call it a dication. If they're separated by a bunch of atoms, where we see intermediates a lot in our mechanisms, where we have nucleophilic attack, and then we have an anion and a cation. But if they're far away from each other, those are called zwitterions. But ylides are overall neutral, so that's part of the definition. So ylides are, I guess an ylide is a molecule that is overall neutral. All right, so we can go ahead and check here at our ylide that we drew before. We see it has 1 plus and 1 minus. Those cancel each other out. So it is overall neutral. So this is checking out with our definition. And the other part of this definition is it contains adjacent atoms with opposite charges. So 1 plus and 1 minus. And we have one final requirement. So let's actually go up and check that. Do we see adjacent charges? Adjacent meaning next to each other. We have a plus next to a minus on the two atoms is phosphine and the carbon. So that goes ahead and tells us that this is correct and a full octet. All right, so this is not having like a radical cation or something like that. We need to think about neutral compounds. Right, turns out you've actually seen ylides before, you just didn't know it. So one example of an ylide that we've seen before is something like nitrobenzene. So a nitro group has a nitrogen that is positively charged and an oxygen that is negatively charged. All right, we take a look, everybody has their full octet. These atoms are adjacent to each other. This is overall a neutral molecule, right? So we've actually seen this before. Carbon monoxide is also an ylide, has a positively charged oxygen and a negatively charged carbon, a lone pair on it. So CO is a really common molecule, right? So now we can kind of take a look at our phosphonium ylide. Right, so we have our phosphine that is positively charged, that is now bound to our carbon skeleton here that is negatively charged. All right, so this is our ylide. Now, to add to the confusion, we actually sometimes draw our ylide sort of in a different way. It's an almost resonant structure in which we can essentially draw it so that this negative charge quenches that positive charge and makes a double bond. So this ylide can also be represented with a double bond to that carbon and R1 and R2. All right, so this is another way we could draw it, but I would say this is easier to see how it reacts. All right, we've made a negative charge. It's pretty easy to see that that's gonna react as a nucleophile. It's a little bit harder for us to see that this is carbon is gonna react as a nucleophile, but when we have this nice negatively charged carbon, it's just a little bit easier to see. So I like to draw these phosphonium salts out, but oftentimes in the chemical literature, we're gonna see these as that double bond. So either one is correct on an exam, and you might see both forms of it. Okay, so we haven't made any olefins. Ultimately, I told you we're going to make olefins or alkenes. Olefins just an old word for an alkene, but this is often called an olefination reaction. So we're going to make alkenes here. All right, so let's going to go through these ylide intermediates. All right, so our next learning objective is sort of the entire reaction. So this is 18Q is our next learning objective. This is the 4 P's. So we are going to look at the mechanism, which is why I wanted to draw out that negative charge for you. So the 4 P's of formation of alkenes. I'm going to put in parentheses olefins, right? That's the same word, but people use this a lot. And this is going to be from aldehydes and ketones. Through Wittig Olefination. All right, so we just call this a Wittig reaction typically, but we'll call it an olefination reaction. All right, so this is kind of like weird looking chemistry, but actually, if we understand how a molecule reacts, no matter if we have some weird atoms in there like phosphine, we can still use chemical intuition to understand what's going to happen in this reaction, all right? So let's start out with the fact that we are going to have our Wittig salt that starts, okay? So we had our Wittig salt, and I'm going to draw it all in blue this time because it's going to turn into a nucleophile. It's not going to be an electrophile. So we already saw that we needed base, right, in the reaction. We've seen this before. I just drew the mechanism of this. We're going to get ready to make our Wittig salt. Got my phosphine. Okay, so my phosphine is still positively charged. We're going to form that anion at our Wittig salt. And this looks like a pretty good nucleophile. All right. So it turns out it's going to act as a nucleophile and an electrophile, which is a little bit confusing. But we can sort of see where the electrophilic portion of this could be and where the nucleophilic portion of this could be. All right. So I'm going to draw our aldehyde or our ketone as our coupling partner. We'll walk through the mechanism of how we end up getting to an alkene. So we're going to take R1 and R2 from our Wittig salt, and R3 and R4 from our ketone or aldehyde. All right, so we're going to get all of our carbon fragments from the ketone and aldehyde. We're taking all of the carbon, and what's left over is going to be this triphenyl phosphine oxide. All right. So the driving force of this reaction is actually formation of that triphenyl phosphine oxide, right? So the P double bonded to O is a very strong bond, right? It's a double bond, and it is what drives this reaction forward. or personal experience, is very hard to purify out of your reaction. All right, so we'll take a look at the mechanism. So first off, the two steps in this reaction are going to be the formation of the ylide. As we said, is this weird compound with a plus and a minus on it. And then the second step of the reaction is the formation of the alkene. Or as sometimes you see it called an olefin. All right, this is kind of like a weird looking set of reactions, but turns out that when we think about this, you know, what are we identifying? We're always trying to look where our electrons are starting from. This looks like a pretty good starting point. Looks like a pretty good nucleophile, it's a carbon ion. We're also always looking for where our electrophile is. So we have a carbonyl carbon, and throughout this entire chapter 18, the carbonyl carbon has been a great electrophile. So let's take a look at the mechanism, keeping in mind, even though these reagents, they may look unfamiliar to us, if we understand the fundamentals of how nucleophiles and electrophiles interact, this mechanism actually doesn't have to be so scary. All right, so let's take our aldehyde. Or a ketone. So if our 3 or 4 is a hydrogen, it's an aldehyde. If they're both carbons, it's a ketone. Now let's take our phosphonium ylide. I'm going to draw it suggestively so we see that we have a negative charge there. Our triphenyl phosphine is positively charged. All right, so you've seen in 2301 a 2+2 cycloaddition. Right, when we took 2 olefins that looked like this, and then we just made some bonds between them. It was harder to see the polarity here. What we ended up with was a cyclobutane. It's harder to see the polarity there. It's like, where are these, what's the nucleophile, what's the electrophile? We're gonna look at a similar mechanism, but it's a little easier to see, all right? This nucleophile is gonna attack the electrophile. And then those, you can either draw this in 1 step or 2 steps, but we can think about that bond breaking between our CO double bond because we've now made a bond to the carbonyl carbon, and we can think about that attacking our phosphine, which is positively charged. All right. So that means we have this interesting intermediate here, where we have a bond to our carbon. And a bond to our oxygen and phosphine. All right, so when we're looking at that, we just identified what the nucleophilic site is and the electrophilic site, all right? So this intermediate is called an oxaphosphatane. So now we've made the appropriate carbon-carbon bond. We can take a look at our product and we can say, okay, I need to make a double bond between our 2 carbons. So the 2 carbons being this carbon and this carbon. I need to make a double bond there, and I need to make a double bond from the oxygen to the phosphine based on our byproducts, right? So using sort of chemical intuition, we can now break apart this oxaphosphatane. We can take the electron density from the phosphine carbon bond, give it to make our double bond between our 2 carbons. And then we can take this CO bond, take that electron density, and give it up to make that O phosphine bond. And believe it or not, what we end up with is our double bond between our 2 carbons. Great. And we ended up with our double bond between our phosphine and our oxygen. And that's the mechanism of the Wittig reaction. All right, so just using chemical intuition, even though these look a little bit unfamiliar to us, chemical intuition is going to be really helpful for us to understand a mechanism that looks unfamiliar. Turns out it is just a nucleophile attacking electrophilic carbonyl, then those lone pair of electrons, or the electrons from that double bond. If you wanted to draw a series of arrows to break this CO double bond and put that electron density on oxygen, and then draw a third arrow, that would be fine too. If that's easier for you to think of rather than taking these electrons in the double bond, it doesn't matter. We get there the same way. All right, so this is the Wittig reaction. So let's go ahead and practice this, all right? So I've only drawn R3 and 4 and 2. Oh, I'm sorry, this should not be R3, this should be R1 here. Sorry about that. All right, so I've drawn all these R groups. What does this actually look like in a real world reaction? All right. So at the end of the day, we can start off with an olefin. So let's start off with something that looks like this. Draw that 5-membered ring better. All right, and then we can have other substitution patterns here. Okay, so from this, we know that the olefination reaction is going to break our CC double bond, right? So at the end of the day, we need one ketone, starting material, and one Wittig reagent. Okay, so let's think about this retrosynthetically. Let's say that, let's number these carbons 1, 2, 3, 4 on this side. Let's say, so we're looking back up at our reaction. Okay, we need a ketone. So let's make carbons 1, 2, 3, 4 into a ketone. All right. Now let's take a look on the other side, and we can label these carbons on the other side, 1, 2, 3, 4, 5. Now we're going to go ahead and we're going to need a phosphonium salt with a 5-membered ring. 1, 2, 3, 4, 5. We have a CH here, and we can have our phosphonium salt. All right, so we just need one ketone and one Wittig salt, all right? This Wittig salt could, of course, have come from, we can do retrosynthesis more. This Wittig salt could have just come from the alkyl halide, right? And our triphenyl phosphine. Right, and then in the forward direction, we would go ahead and deprotonate that and we'd get there. But the nice thing about Wittig reactions is it turns out we arbitrarily decided that this 4-carbon fragment would be our ketone. But what if we decided that that 4-membered or the 4-carbon fragment was our Wittig salt? We could do that as well. So we could say that this is our Wittig salt. That would be equally correct. All right, so we have 2 correct answers in this case. And we can say that our 5-carbon ring could have been from our ketone. All right, so both answers are correct. And we could get to our Wittig salt from the alkyl halide and triphenyl phosphine. Right, so sometimes there are multiple correct answers in chemistry. Now, how we decide this in the lab is the availability of these compounds, seeing what we can buy or we can take off the shelf. All right, so there's a lot of ways you can make Wittig olefination reactions work. All right. Okay, let's practice this with a CHEM. All right. So remember, there's multiple correct answers. So for me, I've been having trouble with CHEM in the app, but if I make it go into a window like in an internet browser, Safari or Firefox or Google Chrome, whatever you use, it's still working better for me. So that's just a little tip. All right, so what do you think could be the starting ketone or aldehyde in this case? I always recommend labeling and numbering your carbon chains. All right, so it's been a slow trickle in. These are sometimes hard to see, but let's see where people are at right now. Okay, so we have a lot of answers here because this is a bit of a challenging question, all right? So we'll go ahead and, let people think a little bit more, but if we take a look at some of our carbons, when we're thinking about this, we split our olefin, and so we need a ketone that is either the entire fragment except for that methylene, or we need that methylene. So I definitely see that it's easier for people to recognize C as one of the correct answers, but going and seeing the other side of this appears a little bit more challenging, all right? So we'll give people another moment to answer, and then we'll go ahead and check in and go through this chime-in question. Right, I don't see anybody else chiming in, so I'll go ahead and close this. Okay, so let's take a look at this compound that we have. All right, so this is our chime in. All right, so we have an olefin, and we have, I'm not gonna draw it in with all of our methyl groups here with the word methyl on it. So let's start numbering our carbons, 1, 2, 3, 4. Then we need an extra carbon at this branch for carbon 5, and then carbon 6. Okay, so in this example, let's go ahead, and we know to make, in the Wittig reaction, we're making a carbon-carbon double bond, so we're gonna go ahead and chop this molecule up at that carbon. So it seemed easier for people to think about the ketone fragment of this longer carbon chain, all right, and replace that double bonded carbon with a ketone. So this is absolutely one of the correct answers. All right, great. So that would mean that our phosphonium salt, in this case, that wasn't the question, but I'm going to write that down for you as well, was going to be just from methyl halide. So we have 3 hydrogens here. You can sort of see that coming from, I'll draw on the hydrogens of this molecule. There's never a problem with doing things like drawing in hydrogens if it's easier for you to see, right? I drew these in, so maybe it's easier to see. We would deprotonate one of these, and we get 1 carbon fragment, and that would be our phosphonium salt. All right, from the chime-in, it was a little bit difficult for people to see that we could just use formaldehyde as our 1 carbon fragment. Right, so this 1 carbon fragment could actually just be from formaldehyde. All right, and then that means that our Wittig reagent our phosphonium salt would come from that carbon skeleton with our 1, 2, 3, 4, 5, 6 carbons. And we would see that we have a hydrogen there, and we can make this from our triphenyl phosphine. Right, we would deprotonate that. Can make that from the alkyl halide. Right, so I highly recommend kind of taking a look and seeing, practicing over and over again. If you chop something up at the olefin, what can your ketones be? All right, so it can be hard to see a little bit, but we've run into this scenario before in this class where we can make something multiple ways. Okay, so we have alkenes here. Thus far, I haven't really worried about substitution patterns. I've had everything sort of be equal, but we know that not all alkenes have symmetrical substitution. So we need to start to think about, I hate to say it, but we need to start to think about stereochemistry here, all right? So learning objective 18R deals with making olefins that could be E or Z. All right, so learning objective 18R is to predict the stereochemistry of the alkene based on ylide identity. Oftentimes we have stereochemistry that's correlated to one component or the other, and in this case, we're thinking about the ylide, that strange plus minus intermediate. All right, so let's go back to our sort of generic reaction, all right? So if we had the retrosynthesis where we have R1 and R2, and we're gonna get that bound to R3 and R4. We can chop that in half, and our ylide, if we go retrosynthetically, our ylide could potentially come from R1 and R2. We have a negative charge there, a phosphine with a positive charge. All right, this is one of our options. R4. So because I have all my R groups are different, 1, 2, 3, and 4, why did I choose R1 to be on the same side to R3? Because we could have the scenario where R1 is on the same side as R4, and these two groups would be flipped, right? So this is when we're thinking about E and Z of our alkenes, isomers, right? We have the highest priority substituents on one side versus trans to each other, and this will give us Z is on the same side, E is on the opposite side, all right? So we need to understand why I chose to do R1 and R3 on this correct side, all right? So stereochemistry can deal with alkenes as well, and this is determined by the electronics, not sterics, the electronics of the ylide. All right, so we have something called a simple ylide. Right, so a simple ylide has alkyl groups. And if you have alkyl groups, you're going to get the Z as the major isomer. All right, I'll give you an example of that, okay? So we have benzaldehyde. Let's start out with benzaldehyde as our source for two of the carbons. And so this is, we can see hydrogen and phenyl are going to end up as either R3 or R4. And so how are these going to be bound? Now let's take a look at an ylide, as I said before, that's alkyl substituted. All right. So you can have triphenyl phosphonium and then a negatively charged there. So this is our simple ylide because it is the alkyl substituted one. And so we are going to get the Z isomer, which means that phenyl, which is the highest priority, and ethyl are going to be on the same side, right? Because the other things on the other side are hydrogens, all right? This is the Z isomer, same side, all right? So we have 2 carbons, 1, 2, that came from our, I'll even label those, 1, 2, 1, 2. And then we have a hydrogen on the other side. All right. So we can also think about, of course, more substitution patterns, but I wanted to simplify it because whenever we're comparing to H, the other thing's going to have the highest priority. Okay. So now we're going to have something called, if we want to get the E isomer, we're going to have something called a stabilized ylide. All right, a stabilized ylide has an electron withdrawing group. Okay, if we have electron withdrawing group, we're going to get an E isomer as the major. I say major because sometimes the selectivity isn't perfect. Okay, so let's see what that looks like. Before we had our simple ylide, we just had our ylide with our ethyl group on it. Pretty easy to think about. Now, what we could have if we had that same coupling partner of our benzaldehyde here, and if our ylide had an electron withdrawing group on it, next to that negative charge, we're stabilizing that negative charge with that electron withdrawing group, right? That's why we call it a stabilized ylide. That electron density is being pulled away, stabilizing it. And in this case, we're going to get the E isomer, right? So instead of having our H on the same side as the other H, we're going to have it here, and we're going to have our electron withdrawing group. All right, and this is going to govern the fact that we ended up with an E isomer, right, on the opposite side. So this is what we're looking at. The highest priority groups are on the opposite side. We have E. Here, the highest priority groups on the same side, we have Z. All right. So an example of an electron withdrawing group that's used a lot is an ester. So maybe we would have an ester here. A negative charge there. It could be a nitro. It could be a cyano. It could be any sort of electron withdrawing group. All right. And this would help to stabilize that charge, right? We know that we could get some resonance structures into there. We could resonate here, and that would allow us to really stabilize this ylide. All right, so let's do a practice problem and see if we can figure out the stereochemistry that we have. All right, so our practice, the stereochemistry. So say I was asking you to make this particular alkene. Just one more carbon. All right, say I was asking you to make this particular alkene. I'm gonna go ahead and say, 1, 2, 3, 4, 5. 1, 2, 3, and then the phenyl ring. Let's just go ahead and label that the 2 sides because we know we're gonna break this double bond here. Okay, so for clarity, let's draw in our hydrogen. So in this case, what we have is our highest priority substituents are on the same side as each other. This is a Z alkene, right? So we know that this came from 2 stabilized ylides. And in this case, we can draw those ylide components. Either way, we can say this side, we have our ylide with our carbon fragment being 5 carbons long. 1, 2, 3, 4, 5. 1, 2 carbons strong. Right, and then we could draw our negative charge here and our phosphine here. And we see that this checks out, right? This is just an alkyl chain, so makes sense that we're gonna get the Z isomer. Right? Now, if we wanted to make the ylide on the other side, we absolutely could as well. We have a carbon chain that is 3 carbons long, 1, 2, 3. And we can go ahead and attach our triphenyl phosphine plus and negative. Right? This makes sense as well, that our ylide was able to form the Z alkene because that is also a simple ylide, right? The definition of our simple ylide is just something that's alkyl substituted. All right, so we can look and identify. Now we might run into a case where we get a Z alkene. Now we have a electron withdrawing group here, and then we would just need to think, well, our ylide needs to be the one that's the simple alkene, right? So we can mix and match if we have electron withdrawing groups. It doesn't matter, but we don't really have to think about, or we really have to think about that stereochemistry for our 2 components. All right, I know it's 2 minutes early, but I'll go ahead and end there because that's all that we have. So I will send an email today with all the exam information.